Um, I said I was going to cover three basic approaches to how to talk about, define, derive things concerning the Dirac delta function. And in the previous video, I covered what I call Dirac's original approach. This video, I'm at least going to start distribution theory a little bit. The Dirac approach was the Dirac delta function has these two properties, just defined that way. And then you use normal calculus to derive other properties. And one of the other properties we really wanted was the sifting property. And to derive it using normal calculus, even though the function is not a proper function, was kind of painful, which kind of led to, it seemed kind of hard. Maybe we ought to just bite the bullet, try real distribution theory, and be rigorous about it. See how bad that is. And I'm not going to say I'm an expert at it. In fact, probably everything I know about it is in this paper by Stephen Johnson of MIT. Here's where it is, at least now on the internet. I'm not going to read this, but what is a distribution? I said a real function is a rule that maps from real numbers to real numbers. A distribution is a rule that maps from functions to real numbers. And I'm just going to say everything is real. We're not going to talk about complex. So that this would be, say, the notation for a distribution f. Phi, the so-called test function, is a normal real function. The distribution of that function gives you a number, a real number. So we call that phi a test function. And distribution theory puts some pretty strict requirements on that test function. Typically, it says it's infinitely differentiable, and it has compact support, which means it's non-zero only in some finite region. Talk about that more later, because that's part of this that bugs me. One of my pet peeves about this. Here's an example of a distribution that's based on a real function f of t. By a real function, I mean a good, proper function. It's this definite integral. You put it in the integrand with the test function. This is called a regular distribution because this f is a good old proper function. Look at what would the derivative of that thing look like. It would mean this or this. And we could use, what do you call it? I forgot the thing we do. The UV thing. Integration by parts. And you end up with this relationship. We want to get rid of this thing. We want this thing to evaluate to zero. There it is, integration by parts. We assume that phi is differentiable. That's required by distribution theory. It just says for this to work, phi must be, in fact, infinitely differentiable. And as long as phi is zero at the infinities, which it must be because it must have compact support, this thing is zero. Phi is zero only, well, it's non-zero over only a finite extent. So it's certainly zero by the time you get anywhere near the infinities. So this is zero. So you end up with this thing that says the derivative of the distribution is minus the distribution of the derivative of the test function. And by induction, you could keep on going. It says your distribution is infinitely differentiable if your test function is. Well, that worked for this regular distribution because this f is a regular proper function. Distribution theory simply requires this property. It's a defining property. It didn't have to be derived. It's a property of all distributions by distribution theory. It's like an axiom. So let's talk about an irregular distribution, and I think I'll save that for another video.